Can I use this?
Yes, you can use that one. Also, the pointer is here. Just a little bit to go on right this one.
Okay. So, good afternoon, everybody, and I go straight to the topic. As you see, this is a collaboration at the origin of this work. Well, you know this person here in particular, since he's one of the organizers of this meeting. Now, what is the idea here? I'm afraid this is a problem. Well, how to exploit the Lagrange points of the Sun-Earth system pair to make experiments in fundamental physics, etc. Well, the idea is to place spacecraft in the Lagrangian points. Well, here you see also L3, even though it's quite complicated to put something there since it is on the other side of the Sun. So mainly the idea is to exploit this, the two triangular and L1 and L2. And the advantage, of course, is that this system is moving rigidly in a sense together with the pair here. Of course, the approximation is that everything is spherical, this is circular, no perturbation from outside, etc., etc., etc. Well, this is acceptable in principle. Of course, this is Newtonian also. General relativity, actually there is no closed solution for the equivalent of the Lagrange points, but with these masses, this is acceptable, an acceptable approximation. The idea is to have something there that simply broadcasts electromagnetic signals. Then you can measure the time of flight from L4 to L5, L5 to L2, etc. The idea is what information can we draw from the fact that we expect the time of flight along closed paths is different according whether you are going right-handed or left-handed. Now, let me continue. Well, it's always the same problem.
You should push this one.
Yes.
I don't know why. What is that? I will help you. Yeah.
Thank you. Well, the asymmetry we expect comes from the presence of a gravitomagnetic field in general. We know that when we consider gravity in the general relativity frame, we know that there is a contribution to the interaction that comes from the motion of the source with respect to the observer, and this is especially interesting when the source is rotating. Here you see, well, a general line element here, and the information is, well, I can go there, I think it's better. Well, you see that the relevant term is this one, the mixed space-time term, which can be interpreted as a vector potential in 3 dimensions for the gravitomagnetic field. When you linearize the Einstein equations, you end up with something which is quite equivalent or even formally equal to the Maxwell equations, and this vector potential goes into, through the curl, gravitomagnetic field. Okay, now what is the importance of this? If you now imagine to have light going around some circuit here in both senses, well, physically this can be anything, can be, light pipe, something like that, can be mirrors, can be transponders in this case. You have a different time of flight, right and left, like that. This is the equivalent of the old Sagnac effect. Poor Sagnac, he was against relativity. He thought this would bar special relativity. Rather, it is a general relativistic effect even, and it allows interesting experiments. You write down the calculation in the proper time of the observer here. You have an asymmetry difference in the time of flight, which is given by this formula here. This is also known as the Lense-Thirring effect, which is the drag of inertial frames due to the rotation of the source of gravity. Now, this is mainly the idea. In terms of the gravitomagnetic field, you have a flux of the gravitomagnetic field across this closed path, and that flux is what measures the asymmetry. Let's go on. The asymmetry is due to the gravitomagnetic field, of course. If you write down a line element considering a weak field approximation, and you assume axial symmetry, and you use, let's say, pseudo-polar coordinates like that, the interesting term here assumes this form, where this is the angular momentum of the main source, the rest are the constants, Newton constant and the cube speed of light. This is the distance from the source, and this is the colatitude. If you are in the equatorial plane, this of course is 1, and so if you are able to arrive to this, you are measuring the angular momentum of the source. This is the same thing, but this little j is just this term here. It is the dimension of a squared length. This is a principle that is being implemented now by a terrestrial experiment under preparation, which uses a ring lasers array. The name is Ginger. It will be working at the National Gran Sasso laboratories with the idea of measuring the gravitomagnetic field of the Earth with an accuracy of 1% or better. This effect has already been measured for the Earth with different techniques using the precession of gyroscopes or even the precession of the orbits of satellites. This experiment has been the first. Gravity Probe B, NASA and Stanford University, the poor accuracy, 19%, then studying the orbits of largest and largest two satellites, an accuracy of 10% has been obtained, and now there is this experiment going on. For the moment, the accuracy is 5%, but the idea is to arrive to 1%. Now, let's come back to our main proposal. The name is Lagrange. The idea is to exploit this Sagnac effect in order to measure the gravitomagnetic field at the scale of the solar system. One of the field, of course, one contribution comes from the Sun, the angular momentum of the Sun, but there is more, since we can expect also a contribution from the galaxy. Of course, because we have matter rotating, a big mass rotating, but if you do the calculation, I quote some number after, this is indeed very little. It is probably impossible to verify its presence. But if you include dark matter and assume that a halo is also rotating, the situation changes, and this is extremely interesting. Let me go to the scheme again, and you see that we have many different closed paths possible, including L3. Well, provided you can put something like that there, you have a triangle, which is the biggest here. But let us limit for the moment to these, which are smaller, but the typical size is the astronomical unit. Of course, the shortest is here, but the rest is more or less of the order of the astronomical units. And let me now put some numbers. The term which is interesting is this, and you may do an example considering this triangle, L4, L2, L5, with the data for the solar system. You see that the asymmetry would be in the order of 4 times 10 to minus 13 seconds. Well, it is a small number, but not so small. Today, with the today techniques and technology, we can do much better than that on Earth. Of course, here the situation is to do it in space. But it is, in principle, easy to arrive to better than 1% of this number. just measuring time, difference in time of flight. So this is the idea. Depends on the quality of the clock, depends crucially on how you can say that you are actually at the Lagrange points and what happens there, what is the motion of your station around these points, etc., etc. But it looks feasible and interesting. Now, what kind of information can we retrieve? We say the angular momentum of the Sun, of course. But the Sun is not a rigid body, of course. It has differential rotation, and the angular momentum depends on the position of the tachocline, so-called, which is a layer, a rotational shear, in between the radiative interior and the exterior, where you have convective motion. The depth of the tachocline is crucial, and the tachocline is important because it controls, in a sense, the production via dynamo effect of magnetic field, the solar magnetic field, and the cycle, 11 years or 22 2 years, depending of the activity of the star. So this is physically interesting information. Then we have galaxy, and the Milky Way in particular. The angular momentum, of course, should produce a gravitomagnetic field, just as anything rotating. The gravitomagnetic field has an importance. You know that the problem is that for our galaxies and the other galaxies also, that we have these rotation curves which are not Keplerian. We have, for our galaxy, beyond 5 kiloparsecs from the center, actually the peripheral speed is almost constant. And this does not correspond to the visible mass. You know that the presence of a gravitomagnetic field could have a role there, because gravitomagnetic field looks like magnetic fields and produces a sort of Lorentz force. If you have something moving, orbiting the center of the galaxy, and you have the gravitomagnetic field, you have an excess radial force, which means that the orbit needs to have a higher peripheral speed in order to be stable. Of course, this can be negligible, real but negligible, or important, depending on how big is the angular momentum, the real angular momentum of the galaxy. If you consider only the visible rotating matter, we may estimate a gravitomagnetic field here at the Sun in the order of 10 to minus 22 seconds. Well, that number is quite a small number in a sense that the terrestrial experiments can measure the gravitomagnetic field of the Earth, which is in the order of 10 to minus 12 or 13 seconds to minus 1. So this is quite smaller. It's not possible to measure something like that, and the effect would be irrelevant. But if you have a halo, which is usually assumed to explain the rotation curves, the halo too should rotate. There is no reason why it shouldn't rotate. It interacts gravitationally with the visible matter. Visible matter rotates, and so does the halo, of course. But if it rotates, since its mass, total mass, is, depends on the models, from 5 to 15 times the visible mass, even more according to the models, you have correspondingly a much higher angular momentum due to the dark matter. And this can become important. Indeed, to explain the excess velocity of the Sun around the center of the galaxy, which is approximately 30 kilometers per second, the excess, well, you need a gravitomagnetic field like this. And the mass of the halo, estimated mass, tells that this is quite possible. And this is within reach of the experiment, because we saw before you thinking to 1% or 0.1% of that 10 to minus 13 corresponds to a field like that. So this is extremely interesting. Other possibilities, if you have the stations there in the Lagrange points, you can ameliorate somehow what you know about the gravitational time delay, the Shapiro time delay. Think, for instance, of having something in L1 and L2. Of course, there is the Earth in between, so you have to think of motions like that, and to accurately study what you do. But if you consider the time of flight here, and you develop this in terms from the geometric term on, you have the geometric term, then the proper Shapiro time delay, then you have a quadruple contribution, the oblateness of the Earth. Further, you have also contribution here from the angular momentum of the Earth, with the two different signs, of course. Here are the numbers. Well, this number is, again, not easy to be measured, but possible to measure. Let's go on. Another interesting possibility, you have to, somehow control the motion of spacecraft in the space, in the solar system. Now we do this from Earth, and you have also some automatic action done on board the spacecraft, considering the orientation with respect to the sky, etc., etc. But the farthest you go, the worse is worse, of course. If you locate the transponders in the four accessible Lagrange points, you can set up an interesting system like this. What is this? Each transponder acts as a sort of artificial pulsar, just pulses, regular pulses, nothing else. You know where they are, of course. Then, in space, you are covering space-time with wavefronts, three-dimensional, in 4 dimensions, three-dimensional wavefronts, and with the conjugated 4 vectors, null 4 vectors. These wavefronts are null, so hypersurfaces. These are null vectors. They cover with a sort of an egg crate the whole space-time. And any observer is moving across this space-time and is crossing the borders of these cells. Each time you cross a border of the one cell, it means that a signal is arriving, a pulse is arriving. You are registering the arrival of a pulse. Then you cross another pulse, etc. If you know what is the origin, this is a trivial geometry. You can use just the numbers 1, 2, 3, 4, 5 as coordinates with the digits after the integer given by the segments. On board, you are just measuring these lines with your onboard clock. Proper time is just measuring this and this and that. So triangles, locally in Minkowski space-time, you solve these triangles and you have 4 coordinates, which are your light coordinates in space-time. Then you can project these coordinates into the fiducial reference frame, say centered on the sun or what you prefer, and that's all. And this can be done on board the spacecraft. No need for intervention from the Earth, from ground, or whatever. If the information is there, where are the stations? And they should be always there. This is the crucial point. And you know the frequency of the pulses of each station. The rest is just a simple linear algorithm. Let's go on. I quote all possibilities. If you consider light in this system going like that, here, but then from here to there, to L1, then to L5, and come back, the same signal, come back to L2, and then again L1, then L4, you have 2 circuits, 2 triangles, and the same pulse is working on right-handed sense in one and left-handed sense in the other. If you combine the two, you are compensating any effect there. And you have what is called the zero-area Sagnac configuration. This was proposed years ago in the 90s on Earth for gravitational waves antennas. Now you can realize something like that over the scale of 1 astronomical unit. And this probably would cost less than the interferometers in space, but I just put there the idea. I'm going to close. The crucial point here is that you are assuming that everything is clear. the stations are in L1, L2, L4, L5. We all know that this is not the case, because your station, your spacecraft will move around the L points somehow, and you must know and control how the spacecraft moves if you want really to arrive to the information you are interested in. Of course, L1 and L2 are surrounded by weakly unstable orbits, depending on the amplitude, Lissajous halo orbits. L4 and L5 are stable orbits, slow stable orbits, and there are many details to study. Here there are many experts in the field, more than I am indeed, and you have to work out all these details in order to be able to compensate or subtract from the information from the signals or the difference you compute in the times of flight to extract what is relevant for you. This means that you need a long integration time, and this means that you have to realize a statistic, repeating and repeating and repeating the experiment. This is just an example that we can skip it. Well, the final conclusion is simple. The idea is not quite sophisticated. It's quite simple. The advantages, if you can put the stations in the Lagrange points, are quite interesting, both from the fundamental viewpoint, the information on the solar gravitomagnetic field, the lens tearing from the galaxy, and the quadruple influence of gravitational time delay, and the implementation of a relativistic positioning system. So, if it is so, it would be worth trying. This is the message.